Hi, welcome to Learning Monkey. I am Raghuveer. In this class we will discuss about how normalizing the data helps gradient descent. This will help you a lot in understanding our next classes that are batch normalization classes, which we discuss in our later classes. So please follow our playlist from the beginning so that you will have a better understanding of the complete deep learning concepts. The link for the playlist is provided in the description below. Coming to today's class, in our machine learning playlist we already discussed about the scaling techniques, min-max scaling, normalizing and standardization technique required for numerical data. So based on the assumption that you already know why we need scaling for numerical data, based on the assumption we are continuing this class. There we clearly discussed about a technique called standardization. The name we are using here is normalization, but usually what we are doing here is standardization. The concept was clearly discussed in our machine learning playlist. If you don't know what standardization means, please watch our machine learning playlist and come back here. So but for terminology purpose we are using the same word which everyone uses this. It's using normalization. Usually they call it as normalization, but what we are doing here is a standardization. So don't confuse with the term normalization and standardization. Here we will call it as normalizing the data, means we are standardizing it. Okay, coming to, let's refresh the concept of standardization by taking an example. Then we will understand what's the use of this normalizing the data in our gradient descent. Let's take an example. This is our example data sets. This is our data points. For understanding purpose we are taking only two-dimensional coordinate system. X1 is one coordinate and x2 is other coordinate. See here our data looks like this, and the data points are like this. P1 is one data point, x1, x2, 2, 5, 2, 8, this is our points, and we are having total m data points. So x1 is one input column, x2 is other input column. For scaling purpose what we have done, we have taken the first column x1 and standardized the data, take the second column x2 and standardize the data. Here we call it as normalizing the data. So we take the first column, normalize, take the second column, normalize. How we done that normalization, that we have to understand. So for the normalizing purpose we are calculating the mean value. Take the first column, calculate the mean. How we calculate the mean? Mu1 is equal to 1 by n x11 plus x12, means we are adding all the points. X1 first data point, x12 means second data point, so on. We are having m data points. We are taking the x1 column and calculating the mean value 1 by m into summation of this, and we are calculating the variance value. We call it as sigma 1 square, that is equal to 1 by n x11 minus mu1 whole square plus x12 minus mu1 whole square plus so on until all the data points. That is how we are calculating the variance value. So sigma 1 square we call it as variance, and sigma 1 is equal to standard deviation. Square root of variance we call it as a standard deviation. We calculate these three values and we use these three values to normalize our data. So what's the equation for normalizing the data? In order to normalize the data, x1 means take each x1i, means take each data point in our first column and we have to normalize. The normalized data we call it as z1i. So z values, z is equal to x1i minus, we are subtracting the mean from each and every data point divided by square root of sigma 1 square. What is sigma 1 square means? Variance. Square root of sigma 1 square means standard deviation. x1i minus mu I divided by, it's not mu I, it's mu1. We are calculating the mean normalizing value for the first column. It's mu I divided by sigma 1 square, means standard deviation, square root of sigma 1 square. Here we are changing the equation slightly. What's the equation here is z1i is equal to x1i minus mu1 divided by square root of sigma 1 square plus epsilon. We are adding some epsilon term. Epsilon is a small value. So why we are adding this term means in order to avoid the division by 0. So for that we are adding a small term. Other than that everything is same. We are calculating z values for x1 column and we are calculating z2 values for x2 column. These are the normalized data points. So if you plot the normalized points, let's take a look at the normalized points. Take the plot of, so this is our original data. What we are observing here is this original data, in this dimension the variance is very large. Variance means how much spread our data is. That is what we call it as variance. In this dimension the variance is very small. This is our original data. So what we are doing here is we are normalizing this data. After normalizing the data, if you plot the data, what happens here is, see here, we are getting a value of mean 0 and variance 1. That is what we are normalizing to, means standardizing to. Any distribution, get it into the mean 0 and variance 1 distribution. That is what standardization to. This up to here we clearly discussed in our machine learning playlist about standardization. So let's observe this. Here in this dimension the spread is much, in this dimension the spread is small. When we normalized the data, what happened? We got a spherical shaped data. With this there is an advantage. What's that advantage? Let's understand it. If you substitute this data, this is not normalized data. If you substitute this data in our loss function, so we know about different loss functions. Let's take one of the loss function. So assume that we are using mean squared loss. If you substitute this data in our loss function, we will form a steep ravines. So what's that ravines were clearly discussed. Steep ravines are formed when you use this original data. Why we are forming this is, so what's the problem with steep ravines? This concept were clearly discussed in our previous class when we discussed about stochastic gradient descent with momentum. Whenever we formed a steep ravines, what happens here is our gradient descent weights will oscillate this side, this side, this side, this side, and it will take a lot of time to convergence. That is the problem when if you form steep ravines. So let's again understand what's this steep ravines, why it is oscillating this side and that side, and it is taking lot of time by taking a paper example, so that you will have a better intuition of steep ravines. So let's take a paper. When you substitute this original data in our loss function, we are forming a steep ravine like this. See, steep ravine means here we are having a small gap, and this side, this is one dimension and this is another dimension. In this dimension the function is having steep means very slope. Steep ravines has been formed. With this we will oscillate this side and this side. Why we are oscillating this side and that side? Let's try to understand mathematically. So whenever if this is with one side we are taking one weight value, on other side we are taking other weight value, we are updating the weights in gradient descent. Whenever we are trying to update the weights of our gradient weights of our equation, based on derivative value we will update the values, update the W values. Whenever you find the derivative of W with respect to the derivative of this function with respect to W1 of this side, so the derivative value here in the steep side will be high value. The derivative value will be large if the function is steep. So why the derivative value is large? This is clearly discussed in the basics in our machine learning. First 13 classes we clearly discussed the mathematical basics. We are not touching the basics. When you find the derivative value here in the steep side, the derivative value will be large. If the derivative value is large, our gradient descent takes long steps. Means our weights move from this side to this side. Again, if you calculate the derivative this side, that's why in the steep ravines our weights are oscillating. So this data, if you substitute this data, our function is forming steep ravines. If you normalize the data, our function is forming like this. This is how the function is. If you update the weights, our weights are moving like this. It is not oscillating here because we are not having steep ravines. That is the advantage of normalizing the data. After normalizing the data, what happens here is we are forming, let's understand with contour plots. So after normalizing, before normalizing the data, the contour plots of our function is elongated one side. It is forming a elliptical shaped contours. Okay, it is elongated one side. means it is having large value this side, and this side we don't have that large value, elongated one side. With this contour plot we are not we are oscillating this side and this side, means it is forming steep ravines. So if you normalize the data, what happens here? We are forming a spherical shaped contour plot, means our weights are updating directly, means our weights are moving directly towards the minimum point. So what happens here? If we normalize the data, we are converging fast. That is the use of normalizing the data in gradient descent. We are converging fast. This point we have to understand. The whole class we discussed because of to understand this point. We are converging fast. If you form a steep ravine, we are not converging fast. This point will help you a lot in understanding in our next classes. What's that is batch normalization. Hope you understand the concept. If you have any questions regarding the concept, please post your questions in the comment section below. Thanks for watching. If you haven't subscribed to our channel, please subscribe to our channel and press bell icon for the latest updates. Thank you.